Welcome to this tutorial for Lab Center's Proteus, version 8.10. This software allows a designer to produce a schematic of an electronic circuit and lay it out on a printed circuit board which can then be sent off for manufacture. It also offers some tools for testing and fault finding such as plotters, virtual multimeters and oscilloscopes. This video will be a basic tutorial to introduce you to the software and cover its basic use, but I'll be covering more features in detail in follow-up videos, so please subscribe if you find this helpful. For the purpose of this tutorial, I'm going to build a simple transistor night light circuit. I'll walk you through the basic features of Proteus, which are used to capture and simulate the design schematic, and then lay the parts out on a PCB so it can be produced. First, open the Schematic Capture tool by clicking on the button at the top. This opens the Schematic Capture pane. You can zoom in and out using the mouse scroll wheel, or press F8 to reset to full size. Select the Component Manager tool and open the library. Here you can search for the relevant parts. For this example circuit, we will need some resistors, which can be found by typing RES and select the desired part from the search results. I will use the default part in this case. Here you can see the schematic symbol. This is how the part will appear on the schematic, and here the footprint. This is how the copper pads will be arranged on the PCB when manufactured. There are a variety of footprints available. 0402, 0603 and 0805 are surface mount chip resistors. There are also a number of leaded resistor models of various pitches. 40 thou is the most common prototyping resistor size, so we will select that by double-clicking and it appears in our active parts library. Next, we need an NPN transistor. I'll use a BC547 here as it is a good general purpose NPN transistor. Double-click and it's also added to the active parts library. We also need a typical 5mm LED, which we can search, double-click to add. And finally, a light-dependent resistor, or LDR. Again, we search, and double-click to add to the main parts list. Click OK to close the search tool. To place a component on the schematic, select it from the active parts library, and click once anywhere on the design pane. The component will hover over the design pane. You can rotate it using the number pad plus and minus buttons on the keyboard. Once you're happy with the position, click once more and the component is placed. You can right-click on the component once placed and change its position and properties. You can flip it vertically or horizontally, you can drag it or rotate it, and you can edit its properties, which is also where you set the value. Place the rest of the components in the desired positions. To move blocks of components, left-click and hold to draw a box around the components. When highlighted, left-click and hold again to drag the components around. Next, to connect the components together using wires, stay in the component management mode, hover over a component pin and you will see a small highlight. Click once and a wire is attached. You can drag the wire to the pin you wish to connect to, you will see another small highlight, click once more and the wire is connected. For nodes, simply follow the same routine. Hovering over an existing wire will also produce a small highlight, where you can then click and attach a wire to it. Next, we can set the resistor values. Right-click on the resistor, go to Edit Properties, and enter the desired value. We will use 200 ohms for the LED current limiting resistor, and 47 kiloohms for the potential divider resistor. The circuit needs power to operate. In the Terminals section, find the power flag and attach it to the power rail in the circuit. Right-click and edit the properties to set the voltage. The voltage must have a polarity specified. I will use positive 5 volts in this case. Next, locate the ground flag and attach it to the ground rail in the circuit. This is necessary for simulation, as the virtual oscilloscopes and meters automatically use the ground rail as a reference. If there is no ground specified, they will not produce a sensible reading, or may even throw an error. Next, we can check the circuit's function using the simulator. The LDR's resistance increases as the light level falls. It makes up a potential divider with the fixed resistor, so this node voltage also increases as the light level falls. When the voltage rises high enough, the transistor is turned on and allows current to flow through the LED. In the instruments section, there are simple voltmeters and ammeters available, which can be used to check the functionality of the circuit. I'm going to add a voltmeter on the base node to test its voltage as the light level changes, and an ammeter in series with the LED. To delete a wire or component, right-click and select Delete, or you can right-click twice as a shortcut. Rotate and drag the meter into place. The LED will only draw milliamps, so enter the ammeter properties and select the appropriate range. In the bottom left are the simulation controls. Click play to simulate the circuit, and the meters display values. While the ambient light level is high, the LDR resistance is low, and the base voltage also reads low. The LED has no current, as the transistor is off in this state. As the light level falls, the LDR resistance increases, and the base voltage also increases. When the base voltage approaches 0.7 volts, the transistor begins to turn on, and the LED current starts to rise. The LED begins to illuminate as you see. Bringing the light level back up causes the transistor to turn off again, and the LED goes off. Click the stop button to halt the simulation. You cannot edit any settings whilst the simulation is running. We can save this project with File, Save Project As, and save in a folder of our choice. I will call this one Example. Navigating to the folder, you can see Proteus version 8 saves the whole project as a single file, which is useful, unlike previous versions which used to save the schematic capture and the PCB layout as separate files. This concludes the tutorial for schematic capture. In part 2 we will cover the PCB layout tool.